Hi everyone, welcome. So this is another data related data analysis type of video, and it's the first in a series of short videos I'm going to record about probability distributions. So I thought I'd record this series discussing some of the more common probability distributions that you use or make use of when fitting statistical models to data. So what I'm going to do in these videos is kind of in Jupyter Notebook using Python libraries demonstrate how you can simulate data that follows certain distributions that you might be interested in, and then you can investigate the behavior of those distributions. Okay, so first of all, I'm going to talk about the most commonly used distribution, which is the Gaussian or normal distribution, the kind of bell-shaped curve. And I'll split coverage of this over a few videos. Kind of the notebook that I've created here, if I scroll down, is quite long, so I'll probably split this up over a couple of shorter videos, so it's more digestible. Okay, but let's get started. So the Gaussian or the normal distribution is a probability model that's used to describe many random variables and phenomena. The frequency of the values of the Gaussian follow what's known as the bell-shaped pattern, the bell-shaped curve. So the normal distribution can be specified using two parameters, a mean and a standard deviation. It's often referred to as a parametric probability distribution. So the normal distribution is the probability model that underpins many commonly used statistical tests, the so-called parametric statistical tests that form the basis of a lot of classical statistics, frequentist statistics, and are used for null hypothesis significance testing. So as I stated previously, the normal distribution, it takes on this kind of iconic bell shape that's symmetrical around the mean. So most of the scores or values are clustered close to the mean, with more rare scores or rarer values the further away you get from the mean. So as the normal distribution has been studied extensively by statisticians, its properties are pretty well understood, and it can be used as a model for kind of discrete and continuous variables. We'll kind of see a bit more of that when we plot these things. So probabilities for the distribution, the normal, can be crudely summarized using what's known as the empirical rule. This is kind of a rule of thumb, and this rule tells us that approximately 60% of scores will lie between -1 and +1 standard deviations of the mean. About 96% of scores will lie between -2 and +2 standard deviations of the mean, and about 99.7% roughly of scores will lie between -3 and +3 standard deviations of the mean. This property and this kind of rule is proved quite useful for frequentist statistical methods such as null hypothesis significant tests, as it allows us to calculate that 95% of scores will lie between -1.96 and about +1.96 standard deviations of the mean. And as for a lot of disciplines, the conventional level of statistical significance is often set at the 5% level, so p is less than or equal to 0.05. It provides a useful way to identify when scores or differences between groups, say, are sufficiently rare that we'd only expect to see them about 5% of the time if the null hypothesis is true. Okay, if that's the case, then the results are often viewed as having reached the threshold for statistical significance, which is an inverse measure of support for the null hypothesis. So such an approach, an important caveat, such an approach assumes that the data is sampled from a normally distributed population for the variable of interest, and that a Gaussian normal model is the appropriate probability model to use, which is not always the case. So in this video, what I'll do is I'll demonstrate how to generate and simulate data that follows a normal distribution, and I'll show how to plot that data, obtain parameters for the data such as the mean and standard deviation, obtain probabilities of scores between given intervals, of values using probability density functions or PDFs for continuously measured variables. Obtain the probability that a variable has a value of x or lower, or the value x or higher using the cumulative distribution function, the CDF. And inversely, I'll also kind of demonstrate how to obtain a given value that is say not exceeded a certain percentage of the time using the percentage point function. So if we wanted to know what's the value that's not exceeded 2% of the time, something like that, you'd use a percentage point function or PPF. Okay, I'm not going to do all that in one video as I stated. So first of all, what I'll do is import some libraries, generate some data, and it can be useful to generate data and know the type of distribution it follows if you're kind of if you're sort of demonstrating or trying to use this type of distribution for educational purposes to teach certain statistical techniques. Okay, so let's get started with importing some software libraries. So I'm going to import pandas as PD, numpy as NP, matplotlib.pyplot as PLT, scipy from scipy.stats. I'm going to import norm, which is going to allow us to fit a normal distribution, and I'm going to import seaborn as SNS. So hopefully people are familiar with this, like pandas and numpy. Pandas is a software library that allows us to handle data frames. NumPy, numerical Python, allows us to do lots of numerical manipulations. Matplotlib and Seaborn are libraries that allow us to plot and visualize data, which is always useful. Okay, so first of all, what I'm going to do is I'm going to generate some data that follows a normal distribution using NumPy, and I'm going to use kind of the numpy np.random.normal method, method or function, and this takes 3 arguments as inputs essentially. One of them is called loc, for location, and that is it's asking you, when you're kind of simulating random data, it's asking you to specify what the mean or the center of the random sample is, what you want to set the mean to. The scale is the standard deviation or the spread of the random sample, and this, as hopefully people are aware, that the standard deviation should be a non-negative value based on the way it's calculated. Okay, and then the size, and that's the size of the random sample you want. So how many rows of participants or how many observations or data points you want in the sample. I kind of use the word participants a lot because I work in a psychology department, and that's kind of mostly where our data observations come from. All right, so I'm going to run this cell, the code in this cell here. So I'm going to generate a normal distribution, and here I'm specifying the loc, which is the mean, the scale, which is the standard deviation, and the size, the number of data points we want. So I'm going to create a new object called normal_dis, so normal distribution, and I'm going to use the np numpy.random.normal function or method, and I'm passing in the parentheses there, I'm passing mean. I'm saying generate some data that has a mean of 5, a standard deviation of 1, and has 100 data points in it. So let's run that. What you see is you get this numpy array. It's printed all 100 data points out for us there. So it's done. It's kind of done what we've asked it to. So this data here, 100 data points, mean of 5, standard deviation 1. It's not a particularly large number of data points, but we can use them. We can plot them using a histogram to see their distribution. Remember, we use this normal function from NumPy, so we've asked for like normally distributed data essentially. So let's run that. What I'm going to do here is plot this data, this array of data, using Seaborn. I'm using the Seaborn sns.histplot, so a histogram, and I've passed as the argument. I've just passed the normal distribution object we created above. There you can see it's created a histogram for us. So it's not perfectly bell-shaped. We've only got 100 data points, but it kind of, I guess you could say, yeah, it sort of looks a little bit normally distributed, but there is a bit of skew there. we might, it looks fairly normal. It's not perfectly bell-shaped. It's never going to be sort of noise in data, and we only used 100 data points. We might be able to safely assume that this distribution will meet the assumption of normality that's necessary. Say we wanted to use this in some sort of parametric statistical test to demonstrate that, or to practice how you do that. But as we're simulating data, we can also increase the number of participants by changing the value we pass to the size argument. So let's kind of create another object called normal distribution 2. I'm using exactly the same syntax as above, the np.random.normal. I'm asking for a mean of 5, a standard deviation of 1, but this time I've upped it to 1,000 observations, 1,000 data points, 1,000 participants. I'm not going to print this one out though, because it'll just be kind of a big long list of numbers, a big long array of numbers. But let's plot that now using, so we'll do the same thing as above, we'll just use a histogram to plot that data. And what we will see is that by increasing the number of our data points, the variable is looking increasingly normal in shape. It's got a much more clear kind of bell shape to it. Likewise, so we've just created a variable essentially there, which we could be using to represent, simulated it, generated, we could be using it to represent something of interest that we're investigating. We could create another variable, but this time pass different values for the mean and standard deviation. So that's what I'll do here is I'll create a new object called normal distribution 3. And I'm using the exact same arguments as above, using the kind of random normal. But this time I'm going to ask for the data to have a mean of 6.3 and a standard deviation of 2.5. So a higher mean and a wider spread. We're still going to use 1,000 data points for this though. And then if we use a histogram to plot that, we can see we've got sort of a, you can see here the scale of the x-axis has changed. We've got values going from -2 to 14 now because we asked for a wider standard distribution compared to the one above, and the kind of mean roughly around here is kind of just above 6. Okay, and it's still fairly Gaussian in shape, but as I said, it's kind of got more spread to the data than the previous example. Moving on from that, what we could do is simulate data. So I'm using a kind of random simulation of data, but create data that follows what's known as the standard normal distribution. So what I'll do here is I'll create a random sample of 500 data points, but we'll give it a mean of 0 and a standard deviation of 1. Okay, so although I'm kind of picking an arbitrary sample size here of 500 data points, the other parameters that I'm using, the kind of mean of 0, standard deviation of 1, will make this a close approximation to a standard normal distribution. Okay, so let's create a new object here in this cell. I'm going to call it stan_norm, so standard normal. Same syntax as before, numpy random.normal. I'm specifying though this time a mean of 0, a standard deviation 1, which is typical of the standard normal distribution for which we use to calculate z-scores and things like that. Remember, this is a randomly generated data, so it's just an approximation that is very similar to a standard normal. Okay, so and we can check the size of the array created using the shape method. Okay, so I asked for 500 observations, 500 data points. So what we should have is a kind of an array that's got 500 rows, one column essentially. So if I run the stan_norm.shape method, you see it tells us we've got 500 rows essentially. So that's correct. That's what we asked for, and we can also obtain some. So we can check how well this approximates the sort of standard normal distribution as well by obtaining some descriptive statistics. for this particular variable, this particular array of data we just generated. And we can see how closely the parameters match the standard. So if I'm going to import statistics as st, so it's the base Python package statistics, and then I'm going to just ask for the mean for this array we just created. So I'm going to use st.mean, and then I'm passing the standard normal variable we just created. And what we're seeing is we get a mean of 0.11. So it's not exactly 0. It's very close, and we can do the same for the standard deviation. And the statistics, the syntax from statistics for that is st.stdev standard deviation. And if we do that, we get a standard deviation of 0.75. So remember, the mean's meant to be 0 and the standard deviation is meant to be 1. So they're not exactly 0 and 1, but we can see that from kind of just using 500 data points. The data that we've simulated here closely follows a standard normal distribution, with a mean very close to 0 and a standard deviation very close to 1. Okay, let's kind of visualize this a little bit. Let's create some plots. So what I'm going to do here is I'm going to use matplotlib to create a histogram showing the distribution of our standard normal data, and I'm going to use this. I'm going to create a histogram, so that will show us the kind of discrete bins that we associate with a histogram like this, but I'm going to overlay over the top using the norm.pdf method a probability density function. So we'll be able to kind of show us what the normal distribution looks like laid over the top. So here I'm creating one figure but with two plots on it. The first one is plt.hist, so a histogram. I'm asking for bin width of 30 bins essentially. And then another one I'm using plt.plot, which gives us essentially a line graph. And I'm using this norm.pdf method. Okay, so if I run this code, there we see, hopefully. So yeah, look, that's kind of what our data looks like. The standard normal 500 data points. The orange line is a kind of standard normal PDF probability density function for the data that follows a standard normal distribution, and our data is kind of very closely centered at 0 with a standard deviation of 1. Okay, so one other way we could plot this to see how close it matches a normal distribution is we could create like a QQ plot, a probability plot. So to do that, I'm going to kind of import stats models, and I'm going to use the QQ plot method from stats models. So I'm going to import statsmodels.api as sm, and then we're going to use sm as the nickname, the abbreviation, sm.qqplot. Okay, so let me run this code here, and there we go. What you see essentially is, so we've got the diagonal line. It shows our theoretical quantiles. Oh, I've spelled that wrong there. Let me run that again because that looks terrible. Theoretical quantiles. There we go, spelled correctly now. So we've got our sample quantiles, theoretical quantiles, and the diagonal 45-degree line, the sort of a normally distributed plot, the data points would sit neatly along this line, and you can see they largely do. There's a little bit of deviation away at the edges, so this edge behavior, that's often the case with with data distributions. But yeah, so what we can see from those two plots is that the variable we created corresponds very closely to a standard normal distribution. It's not perfect, as we've got a fairly small sample size, 500 data points. The histogram has a shape that is close to a Gaussian bell shape, and if we inspect the QQ plot, we can see that most of the data points sit along that diagonal line, indicating that the actual and predicted values for a normal distribution are almost identical. So in the above examples so far, I've used numpy to simulate data for various sample sizes and specified that the data should follow a normal distribution. Obviously, the larger the sample we use, the more closely our simulated data will match a normal distribution. I've also looked at ways of checking the data through descriptive statistics and visualisation. So we obtained the mean and the standard deviation, and then we used histograms, probability density function, and a QQ plot. This is useful function, but mostly when doing some sort of statistical analysis or investigating a research question, we want to we have data that's been recorded for multiple variables, and we want to investigate the relationship between those variables. So when we're simulating data like this, we often want a data frame that consists of multiple variables, and not just just create one variable as such. To investigate its properties. But we can extend these techniques that we've used here by simulating multiple variables and specifying the parameters we want. And then we can combine them into a pandas data frame. Okay. When we're doing that, we probably need to make sure we create variables that are equal sizes, so they have the same number of data points to avoid missing data on a variable, say, with a smaller sample size. But that's what I'll cover next. So this is all I'm going to cover in this video. It's already 20 minutes long. But next I'll sort of demonstrate how to simulate multiple variables and combine them together into a pandas data frame. Okay, I hope this was useful and interesting. It can be useful at times when you can't obtain data sets. So often getting a data set to demonstrate some sort of test for teaching can be quite difficult. When you can simulate data like this, you can give it the properties you want, and then that can be used kind of for educational purposes, essentially. Okay, so next video I will demonstrate how to create a data frame from a series of simulated variables. Okay, thank you for watching. I hope this was helpful.